Imagine a cosmic crime scene 1,400 light-years away, where a stellar corpse is slowly devouring the frozen remains of a Pluto-like world. This isn't science fiction. It's the remarkable discovery made by astronomers using the Hubble Space Telescope. Today, we're diving into one of the most fascinating detective stories in modern astronomy, where scientists piece together evidence of water-rich worlds beyond our solar system by studying a stellar cannibal. Our story begins with WD 1647 plus 375, a white dwarf star that immediately caught astronomers' attention. White dwarfs are the dense, hot cores left behind when sun-like stars exhaust their fuel and shed their outer layers. They're essentially stellar fossils, extremely hot and typically composed of hydrogen and helium. But WD 1647 plus 375 was different. When researchers led by Snehalata Sahu from the University of Warwick analyzed its light using ultraviolet spectroscopy, they found something unexpected. Instead of the usual clean hydrogen and helium signature, this star's atmosphere was contaminated with carbon, nitrogen, sulfur, and oxygen, what astronomers call volatiles. This discovery immediately raised questions. How did these elements get there? The answer lies in understanding white dwarfs as cosmic crime scenes. When objects venture too close, they're torn apart by the star's immense gravity, leaving chemical fingerprints in the stellar atmosphere. Think of white dwarfs as celestial forensic labs. When asteroids, comets, or planetary fragments fall into these stellar remnants, they leave chemical evidence of their composition behind. We often see signatures of rocky material, calcium, iron, and other metals. But finding volatile-rich debris? That's incredibly rare. The smoking gun in this cosmic crime scene was nitrogen. The material being consumed by WD 1647 plus 375 contained about 5% nitrogen by mass, the highest nitrogen abundance ever detected in white dwarf debris. This is a telltale sign of an icy, water-rich object, but nitrogen wasn't the only clue. The star's atmosphere contained 84% more oxygen than you'd expect from rocky material alone. Combined with the nitrogen signature, this painted a clear picture. WD 1647 plus 375 wasn't just consuming any old space rock, it was devouring something icy and water-rich. The scale of this cosmic feast is staggering. The star has been consuming material at a rate of 200,000 kilograms per second, equivalent to an adult blue whale's weight every second. And this has been going on for at least 13 years. Based on this consumption rate and duration, astronomers calculated that the original object was at least 3 kilometers across, roughly comet-sized. But here's where it gets exciting. This 13-year observation window might represent just a tiny fraction of the total accretion time. If accretion has been happening for hundreds of thousands of years, the original object could have been up to 50 kilometers in diameter, weighing a quintillion kilograms. That's not just a comet, that's dwarf planet territory. The chemical analysis revealed something remarkable. This object was approximately 64% water by mass. Its ice-to-rock ratio, 2.5, is higher than that of typical Kuiper belt objects in our solar system, suggesting it came from the crust or mantle of a Pluto-like dwarf planet. Professor Boris Gensika, one of the study's authors, believes they've found evidence of the first confirmed Pluto analog beyond our solar system. The nitrogen-rich composition, high predicted mass, and exceptional ice content all point to a fragment of a dwarf planet similar to our own Pluto. This discovery has profound implications for our understanding of planetary systems and the potential for life beyond Earth. In our solar system, comets and icy planetesimals are thought to have delivered water to Earth, the essential ingredient that made life as we know it possible. Finding evidence of water-rich, icy bodies in other star systems suggests that the building blocks for life might be more common than we thought. These objects could have served the same water delivery role for planets in distant systems that comets served for Earth. What makes this discovery even more significant is the method used to find it. Only ultraviolet spectroscopy can detect these volatile elements, especially nitrogen. This technique will be crucial for future searches for the chemical building blocks of life around other stars. One mystery remains. Did this Pluto-like object originally form in the planetary system around WD 1647 plus 375's predecessor star, or was it an interstellar wanderer captured from the depths of space? Either scenario has fascinating implications for how icy bodies move through our galaxy. This cosmic crime scene has been solved, but it's opened up new questions about the prevalence of water-rich worlds throughout the universe. As we develop more sensitive instruments and continue surveying white dwarfs, we might find that the ingredients for life are scattered throughout the cosmos, waiting to be discovered in the chemical fingerprints left behind by these stellar cannibals. The next time you look up at the night sky, remember that somewhere out there, ancient stars are slowly consuming the frozen remnants of distant worlds, leaving behind clues about the potential for life in the universe.